So to start off with section 1.2, the first thing that I want to make note of is as you're going through these notes, I highly suggest that you are writing down these rules, writing down the examples, just as if you were in a classroom to really give you the best chance possible to understand this material. So to start off with, section 1.2 is all about our review of exponents. So the first rule that we'll talk about with exponential rules is b to the m times b to the n, meaning if you have two values with the same base, so the base is b in this case, and you're multiplying them together, then our rule says you keep that base, b, and you add the exponents together, m and n. So you get b to the m plus n. Likewise, if you have a to the m divided by a to the n, so you have the same base again, a and a, then our rule says that you are going to subtract the exponents, a to the m minus n. Just remember in mathematics, it is almost always the case that multiplication matches with addition and division matches with subtraction. So that's just a quick way to memorize these rules. From here, we have that b to the 0 power for any value b is equal to 1, as long as b does not equal 0. So 0 to the 0 power is not 1, but anything else to the 0 power is 1. From there, we have b to the negative n. So if you have a negative exponent, then you can always take that exponent and make it positive by putting the base to the denominator of your fraction. So b to the negative n equals 1 over b to the positive n. Again, b cannot equal 0 though. If you did have 0 to the negative n and you flipped it over, you'd get 1 over 0, which is undefined, so we can't do that. Note that this rule also goes backwards. If you had 1 over b to the negative n, you can flip it up to become b to the positive n. So negative exponents allow you to go from the top to the bottom or the bottom to the top of your fraction. The last three rules are all pretty similar. We have a times b all to the m power is equal to a to the m times b to the m, meaning whenever you have multiplication and with that multiplication you're raising it all to one power, you can distribute the power to each term. So we get a to the m times b to the m. If you already have an exponent when you're distributing that power, so like here, a to the m all to the n, then when you distribute that exponent, you will multiply your exponents together. So a to the m all to the nth power is equal to a to the m times n. So likewise, if we had the same thing here, ab to the m, but it were more like a to the m, b to the n, all to the p power, then when we distribute this exponent, we are multiplying it to each of these exponents, which gives us a to the mp times b to the np. Okay, so remember that's the most common mistake that comes up with these types of problems. People typically add it, but remember you are multiplying it. Anytime you have an exponent raised to another exponent, you multiply them. And our last rule, well, it says just like if you're multiplying, you distribute the exponent. If you are dividing, you also distribute the exponent. So a over b all to the n power, you distribute the n, which gives us a to the n over b to the n. Okay, so now that we have our rules, let's go ahead and try some examples with these. So first off, we have x to the 10th times x to the 3rd. Notice we have the same base x, so we can apply our exponent rules. So going back to those rules, hopefully you have them written down. If you don't, I'm just going to try to fit them into the image a little bit here. Notice that this matches rule number 1. Rule number 1 says if you're multiplying with the same base, you add the exponents together. So we're going to keep that base, x, and we are going to add 10 and 3, which gives us x to the 13th power. And that's it. X to the 10th times x to the 3rd is equal to x to the 13th. Now let's go ahead and try the second problem. Here we have z to the 7th over z to the 11th. Notice that this starts off with rule 2. We have some base in the top and bottom with an exponent on each one, so our rule says we subtract the exponents. So in this case, we are going to find z to the 7 minus 11. You always subtract the bottom from the top, which gives us z to the negative 4. But we aren't done if we have a negative exponent. We still have to simplify this a bit. So notice that takes us to rule number 4. If you have a negative exponent, you can flip it. You can take the value that's being raised to the negative exponent and put it in the denominator and give it a positive exponent. So this becomes 1 over z to the positive 4th power. And that is the simplified form of z to the 7th over z to the 11th. All right, so from here, I'd like you to take a moment to try out this problem. Go ahead and pause the video, see how far you can get through it, and then we'll try it together. Okay, so trying this together, the first thing that we notice we can do here is to apply our Rule 5, distributing the exponent. So we will distribute this 4 to each of our exponents, which gives us x to the 3 times 4 is 12, times y to the 2 times 4 is 8, all over x to the 3 times 5, notice that's rule 6, we're just multiplying the exponents, gives us x to the 15th. And now from here, we can simplify a little bit more because we have an x in the top and bottom, which means we can apply rule 2, subtracting our exponents. So when we do that, there are a lot of ways to go about this, but the way that I've always found easiest is to just bring everything up to the numerator and then move it back to the denominator if it has a negative exponent. So in this case, what I mean by that is x to the 12th over x to the 15th. We're going to subtract our exponents, which gives us x to the 12 minus 15 times y to the 8th. Simplifying that, we get x to the negative 3rd over y to the 8th. And now, notice we have a negative exponent, so we have to apply rule 4. So we will bring that exponent down to make it positive, which leaves us with y to the 8th over x to the third. Notice the y to the eighth did not move because it does not have a negative exponent. You only move the terms that have the negative exponents. Always be aware of that. So just a quick example of that, I'm just going to write this off to the side. It has nothing to do with this problem. If you had something like 2x to the negative fourth, and you were simplifying that, you would only bring the x to the denominator, meaning the 2 would stay in the numerator. You would be left with 2 over x to the positive fourth. The 2 does not have a negative exponent. The only way that that negative would be attached to the 2 is if the problem starts by explicitly showing parentheses containing the 2. In this case, the 2 has the negative exponent, and you would move it down to the denominator with the x. Okay, so again, this has nothing to do with this problem. I'm going to cross this off to avoid any confusion, but it just shows you to be aware which values get moved when you have a negative exponent. All right, so I want to go through a couple more examples of this. From here, we now have 6x to the fifth, y to the negative fourth, z to the negative second, all to the negative second, over x, y to the negative first, z to the negative third, all to the negative third. To start simplifying this first, we will begin by distributing this negative exponent and this negative exponent. Regardless of whether they're positive or negative, we are going to distribute them. Another way that you could approach this, just in case you had a different idea of how you wanted to do this, it is perfectly okay to begin by flipping both the top and bottom values to get rid of these negative exponents and make them positive. That would work out just as well. So there are a lot of ways to solve these problems. But again, I'm going to start by distributing the negative exponent to every term. Remember, when we distribute these, we are multiplying them to the exponent that is already there. So in this case, there is technically an exponent of 1 on that 6, since we didn't have one yet. So that gives us 6 to the 1 times negative 2 is negative 2. X to the 5 times negative 2 is negative 10. Y to the negative 4 times negative 2 gives us y to the 8th. And z to the negative 2 times negative 2 gives us z to the 4th. All over, again, this x, just like the 6, does not have an exponent, which means there's technically an exponent of 1 there. So 1 times negative 3 gives us x to the negative 3. Y to the negative 1 times negative 3 gives us y to the positive 3. And z to the negative 3 times negative 3 gives us z to the 9th. Now that we've done that, it's just a matter of combining like terms to finish simplifying this. So, notice we have an x in the top and bottom, y in the top and bottom, and z in the top and bottom. So we're just going to go ahead and apply Rule 2 from our exponent rules and just subtract all of these exponents and put them all in the numerator. So we leave the 6 to the negative 2 since it didn't have anything to subtract with. From here we have x to the negative 10 minus negative 3 is the denominator's exponent. Then we have y to the 8th minus 3. And finally, z to the 4 minus 9. So we get 6 to the negative 2 times x to the negative 10 minus negative 3. Well, when you're subtracting a negative, it's the same thing as adding a positive. So negative 10 plus positive 3 would give us negative 7. Times y to the 8 minus 3 is 5. Times z to the 4 minus 9 is negative 5. And finally, from here, we're going to get rid of the negative exponents. So this 6 to the negative 2 is going to go down to the bottom of a fraction. So we get this x to the negative 7 going down with it because it also has a negative exponent. And finally, this z to the negative 5th will also go down, but the y to the 5th will stay exactly where it is because it already has a positive exponent. There's no need to move it. So we get left with y to the 5th in the top, or in the numerator, over 6 squared x to the positive 7th z to the positive 5. And at that point, we can call this problem finished. Technically, we could take this 6 squared and multiply it out to give us 36, but it is perfectly okay to leave it in this form, as these problems are just about applying exponential rules, and sometimes you will end up with something like 2 to the 20th power. And that is completely impractical to multiply out. It will give you an extremely large number. So it's perfectly okay to just leave these as they are. With that, I would like you all to try the next problem. 2 to the negative 4th times a to the 2, or a squared, times b to the negative 1st, times c to the negative 2nd, all to the negative 2nd, all over 2 to the negative 1st, a to the negative 2nd, b times c to the 4th, all to the negative 4th. Take a moment, pause the video, see if you can get through this one, then we'll try it together. Okay, so going through this, just like last time, the first thing we're going to go through is distributing out these exponents, the 2, the negative 2 that is, and the negative 4. So we're going to distribute this negative 2 to each of our exponents, and then distribute the negative 4 to each of our exponents. So starting in the top left, 2 to the negative 4th to the negative 2. Remember, we multiply our exponents when we distribute. So this gives us 2 to the negative 4 times negative 2 is positive 8. Times a to the 2 times negative 2 is negative 4. Times b to the negative 1 times negative 2 is positive 2. Times c to the negative 2 times negative 2 is positive 4. All over 2 to the negative 1 times negative 4 is positive 4. Times a to the negative 2 times negative 4 is positive 8. Times b, remember there is no exponent here, so there's technically a 1. So b to the 1 times negative 4 is negative 4. Times c to the 4 times negative 4 is negative 16. And now we can begin simplifying using Rule 2 from our exponents. We're going to subtract the exponents of all our like bases and put it all into the numerator. So we have 2 to the 8th divided by 2 to the 4th. So we get 2 to the 8 minus 4 times a to the negative 4 minus 8 times b to the 2 minus negative 4 times c to the 4 minus negative 16. Simplifying all of these, we get 2 to the 4th times a to the negative 12th times b to the 2 minus negative 4. Remember, we can change this to plus a positive, so that gives us b to the 6th. And again, minus negative 16 becomes plus positive 16, so we get c to the 20th. And finally, our last step is to bring this negative exponent down while leaving all the positive exponents exactly where they are. So we get 2 to the 4th times b to the 6th times c to the 20th all over a to the positive 12th. And again, you could multiply out that 2 to the 4th, which would give you 16, but there's no need to do that. This is just about simplifying exponents. All right, so the last thing we have to cover in section 1.2 is scientific notation. Scientific notation is a very real-world application of these exponential rules. It's very useful to us, especially if you're taking any type of physics class or chemistry, things like that. Instead of writing out these numbers that are like 7 trillion times 84 trillion, you can rewrite that into a very easy to read format. So, to define what scientific notation is, we say scientific notation is the form a times 10 to the nth power, such that a is greater than or equal to 1, but less than 10. In other words, it's a single-digit number. And n, the exponent, is in the integers. This double Z looking symbol means integers. Integers are any whole number you can think of with a positive or negative attached to it. So just a few quick examples: negative 3, negative 2, negative 1, 0, 1, 2, 3, 85, negative 1 million, things like that. All right. So the process to convert to scientific notation, so to convert some number x to scientific notation, the first thing that we have to do is find the decimal in our number x and move it to the left or right until a is found. So if we're dealing with a whole number, so something like 500, the first thing to note is that the decimal is always at the very end of the problem. So if we were dealing with, again, 500, then the decimal is technically right here. Whenever you're dealing with any whole number where you don't see the decimal, it's always at the very right of the problem. Okay, from there, we're saying that we have to move the decimal until a is found. Remember, a is some number greater than or equal to 1, but less than 10. So we're going to keep moving the decimal until we get a value between 1 and 10. So we say that n, our exponent, starts at 0, and whenever we move the decimal to the left, we're going to add to n. However many times we move it, that's how much we add to n. And if we move the decimal to the right, we are going to subtract from n that many movements. And when you follow this whole process, you will get scientific notation. So let's go ahead and give this a try. Let's convert 8,531 to scientific notation. So the first thing we should make note here is that the decimal isn't shown in the problem, which means it's technically at the very right. Now that we have it, we need to move this decimal until we get a number that is greater than or equal to 1, but less than 10. So we're going to move it once. Note that we now have 853.1. That is not between 1 and 10. We'll move it again. We now have 85.31. Closer, but still not there. One more time, we now have 8.531. That value is between 1 and 10, so that is our value of A. 8.531 times 10 to the, and now note we moved this decimal 3 times, and we moved it to the left, so we are going to add 3. So we get 8.531 times 10 to the positive 3. If we moved it to the right, we would have negative 3. And this is the scientific notation of 8,531. 8 times 8.531 times 10 to the third power. From here, we are going to convert negative 177.23 to scientific notation as well. When you're dealing with a negative in your problem, just ignore it until the very end. That's all you have to do for scientific notation. So, starting off just like last time, we take our decimal. We need to move it to get a number between 1 and 10. Since we have a larger number than 10, we are going to move this decimal to the left again. When we move it, we get 17.723. That's still not between 1 and 10. We move it again, we get 1.7723. This is between 1 and 10, so we have 1.7723 times 10 to the, notice we moved it 2 times to the left, so we get a positive 2. And now the last step, we put our negative in the answer. The scientific notation of negative 177.23 is negative 1.7723 times 10 to the second. Alright, so for this last one, I'd like you to take a moment, try to pause the video and see what you can do with this problem, and then we'll try it together. Okay, so going through this together, we need to find our value for A. We have our decimal here. To get a number between 1 and 10, we need to start moving the decimal to the right. When we move it once, we still don't have a number between 1 and 10. Again, we still don't. But one more time, and we now have 5.24. That is between 1 and 10, so we get 5.24 times 10 to the, notice we moved the decimal 3 times, and because we moved it to the right 3 times, we are going to have 10 to the negative third power. So 5.24 times 10 to the negative third is the scientific notation of 0.00524.